So today I'm going to be talking about image-based approach to large-scale visualization, or cinema science. So why cinema? Or what is it? It's probably no secret that modern simulations can produce very large data sets. Very large data sets in the sense that it's difficult to render them, to visualize them, because the amount of data is so large. So let's say you're running a large galaxy formation simulation, large fluid dynamic simulations, etc. And by the way, everything I'm going to show you today also applies to empirical or observational experimental data as well. If your data is very large, in the sense that it's very difficult to visualize it, and if you load it, let's say in ParaView or Visit, it takes just a very long time to visualize it. So this is where Cinema can help. So you can see that, if the data set is so large that it takes many seconds or many minutes to render an individual frame, what you can do, you can start, let's say you're working in ParaView, you can start ParaView in the client server mode, and then you start a server on an HPC cluster on a very large machine. Perhaps you start the server in parallel, let's say ask for around 64, 128 CPU cores, and then you start ParaView on your computer, on your laptop, and then from your computer, you connect to the ParaView server, and then you run your large rendering or data analysis and rendering pipeline on a large machine. So that will work just fine, and that way you can actually speed up your rendering. But you don't always have access to a very large computer for interactive visualization. And also the way we suggest to use to do rendering on large computers is not to rely on interactive rendering all the time, because that will imply that you're actually sitting on a lot of resources and you'll be using a lot of resources all the time. But rather, let's say if you want to create a visualization pipeline, you can start a client server setup, let's say in ParaView or in Visit, asking for, let's say, 128 CPU cores, and then you work interactively, you load your data, you visualize your data, and then you export it as a Python script. I'm going to show you examples today. You export it as a Python script, then you copy that script to the HPC cluster, and then you run it as a batch job, right? So instead of doing everything interactively by client server, you can run your very large visualization as a batch job on a large computer. But Cinema actually lets you help with these workflows. So the idea of Cinema is that instead of live rendering, you can actually pre-render all images for your full set of viewing parameters, let's say different angles, different theta phi angles. You can turn on and off different views, different representations, etc. And then so you have a large number of, let's say, several hundred, several thousand images that you pre-render. And by the way, you can pre-render these images via batch rendering on an HPC cluster. And then you load these images into a specially formatted, you put them into a specially formatted database, and then you load this database into a Cinema-enabled environment, let's say running in a web browser or in a standalone application. And then you are playing with this visualization as if you were doing visualization live, but in fact, everything is pre-rendered and it's just viewing a recorded database. So by the way, one easy way to reproduce this problem when visualization takes a very long, actually, let me put it into the slide mode. When visualization takes a very long time is try to switch on ray tracing in let's say, ParaView. So in ParaView, there's this wonderful ray tracing library called Osprey. It's an open source library from Intel, and it lets you create photorealistic images. And with Osprey, the thing is that typically, in order to get a very nice image, you need to have many samples per pixel. So let's say 30 or 50 or 100. And so when you have just one sample per pixel in your environment, everything is perfectly fluid, well, almost fluid. So you might see, some delays. Maybe it'll take 100 or 200 milliseconds to render a single frame. But if you want to improve the quality of your visualization with Osprey ray tracing, I'm going to show you an example today. Then you can enable multiple samples per pixel, let's say 30 samples per pixel. And that way, each pixel, well, basically, ParaView shoots 30 rays per pixel. And that takes a while. So that creates really high quality images, but it's not going to be interactive. So if you enable this, multiple samples per pixel and try to do interactive rendering, everything is going to be very slow, because as you try to, let's say, rotate your object in ParaView interactively, all those intermediate frames, ParaView will try to render them with 30 samples per pixel as well, and it's just going to be very, very slow. And Cinema actually can help you here really, really easily, because you can pre-render all these images and then load them into a Cinema environment and then play with it as if everything was rendered interactively. So Cinema, let's talk about the history of Cinema a little bit. So Cinema, the original Cinema project was released almost 10 years ago in 2014. And it was created by Kitware. So they are the makers of VTK library, Visualization Toolkit library. and ParaView and a lot of other wonderful open source visualization packages. So they released this cinema environment, so an image-based approach to extreme scale in situ visualization and analysis back in 2014. And what it is, so back at the time, almost 10 years ago, I played with it, and it's essentially a JavaScript framework for creating a visualization website, well, visualization pages that you open in your browser, and there you can explore these, cinema databases interactively. So unfortunately, it looks like this package is no longer maintained. So the last update was in March 2015, almost 9 years ago. And yeah, so I don't think that original part. I mean, it was wonderful at the time, but I'm not actually sure if it works any longer because it's been almost 9 years since it was last updated. But fortunately, there are a number of follow-up projects. So the biggest one of them is so-called Cinema Science. So if you click on this link, by the way, all links in the slides are clickable. So if you click on this link, can you see my web browser, by the way? So I'm showing you the web browser on top of my full screen. I think that should work. Let me know if you cannot see the web browser. So there is this web page, Cinema Science, which is primarily centered around this Cinema Science or Cinema Sci Python toolkit that is open source package available on GitHub. They have pretty good documentation, but documentation is limited only to this Cinema Science toolkit, not to everything else they do. So read this documentation, and it looks like it's more or less, currently maintained, well, almost. So last update was in July 2022, and so this is the project from this data science scale group at Los Alamos National Lab, and most recently they released another package. So actually, it's not on the website, but if you go to GitHub and look at the list of contributors, most contributors actually from the Los Alamos National Lab. So this is what is called PyCinema, so Python Cinema, and they call it Cinema Engine version 2.0. So I guess this is going to be a replacement to the original Cinema Science project, and it's currently active maintained. So last update was in May of this year. And what it is, it's essentially a viewer as well as a collection of Python functions. So it's a Python library for manipulating these cinema databases and pre-rendered images via filter graphs and the so-called workspaces. So I'm still not quite sure what to think of this. So I played with this a little bit, these filter graphs and workspaces in the Cinema standalone application. And I think it has some potential, but I think it's right now, it's not yet ready, in my opinion, for end use. So, I mean, but there's a lot of potential. But today I'm not going to talk about it. So I'm going to be concentrating mostly on the viewer and how to actually create these cinema databases. All right. So all of these views that I mentioned, there are a few others that I'll mention as well. They support these cinema database. So the latest version of the cinema database is spec-D. So that's the fourth iteration, A, B, C, and D, the fourth iteration of a database. And it sounds very complicated, but it's actually not. It's really, really simple. So the idea is that any cinema database has a bunch of pre-rendered images. Perhaps it has also data as well. So cinema supports not just images, but data as well. And you put all these files into a directory. Typically, it should have an extension .cdb. Directory name should have an extension .cdb, but not necessarily. So you can actually put it in any directory. And then, so inside this directory, I have a bunch of data files, a bunch of images. And then you have these comma-separated value file, .csv file called data.csv. And in Cinema, it has to have exactly this name, so data.csv. And what it contains is a list of all data files of all images, as well as the list of parameters that correspond to that image. So let me show you an example, and it'll become very, very clear. So here I'm going to go to a directory that is actually a copy of a GitHub repository. So if I go back to this GitHub, let's see where it is. Actually, I think I have it a little bit further. So it's the PyCinema. It comes with, well, there's a PyCinema GitHub repository, but there's also PyCinema-data repository that contains a nice set of tutorial cinema databases. So let me open my terminal and let me go into that directory. So I hope you can see the font is big enough. So here I have a bunch of tutorial databases, and one of them is called sphere.cdb. So if actually, let me show a tree on sphere.cdb, and you can see what it contains inside is a bunch of subdirectories. So there is a single running variable, which is the azimuthal angle. You'll see in a second what it looks like. And so there is a single subdirectory. So there's image subdirectory and then a single subdirectory inside that image directory that contains one PNG image per file, right? So these correspond to different azimuthal orientations of your visualization. And then in the top level directory, sphere.cdb, there is a file data.csv. So if I display it, this is what it looks. This is what it looks like, and it's essentially a spreadsheet, right? So it's actually a CSV file that you can easily write in this format from pandas in Python. So it contains a couple of parameters, theta and phi, but you can actually see that all thetas are the same. So theta is always 0, and then phi is the azimuthal angle that runs from minus 180 degrees to 162 degrees. So it's corresponds to rotation of your rendered object around the vertical axis. So there's essentially a single running parameter, and then there is an image that corresponds to each value of this parameter, right? So once you load this into a viewer, you will get you will actually get a nice spinning visualization. So this is what essentially this SpecD Cinema database looks like. And then how do you visualize it? Well, there are many viewers, so I'm going to talk about a couple of them. So the original viewer, version 1.0, that was updated last year on GitHub. So that's the Cinema Sci Python toolkit, and the way you install it is really simple. So I suggest that when you play with these toolkits, you compare, especially if you compare different toolkits, you probably want to install them into separate Python environments, because otherwise you will get collision between different versions of library. And also they have they come with a Cinema command line tool that is called Cinema, both in Cinema Sci and in PyCinema. So it's a very good idea to install this as part of a virtual environment which isolates each library. So anyway, so here's just an example how I would install it on essentially any computer. So here I create a virtual environment called Cinema Sci in my home directory. And then I install this package Cinema Sci. All I need to do is just say pip install Cinema Sci, and we'll install not just this package, but all dependencies as well, including Jupyter. And then if you want to follow all the tutorials, I won't show you today, but if you want to follow the tutorials, you can also install the OpenCV Python package that is necessary for some of the examples. So if you want to run this Python toolkit inside Jupyter Hub, then also you need to enable this Cinema Sci library inside your Jupyter Hub installation, as well as install Jupyter Hub widgets library, right, to be able to work with sliders. So you need to install them and to enable them as well. But this is optional in the sense that you only need to do this if you want to work inside Jupyter Hub. All right, and then once it's installed, once you source the environment, so it's very important to say source, you source the environment. And then there are a number of ways you can use this. So one, you can start a Python server. So cinemasci.server, you start it from Python, you serve it on a given port, and then you're looking at a given database, right? So let's actually see what this database looks like in this Cinema viewer. So I'm gonna go to TMP folder, and then I'm just gonna enable, so I'm gonna say source, oops, I cannot do it here, sorry. I need to exit full screen to be able to copy from the PDF. So let me source this environment. Okay, great. And so now I can actually run this line. So here I'm serving on port 8200. I'm serving this data set that I just showed you what it looks like inside the terminal. So data comes from this directory, from this database, and then I'm launching what is called a viewer called view. There are a couple of views, so I'm going to show you another one in a second. So here we're launching it, and then it's going to serve on this port 8200 on my computer, and this is what it looks like, right? So here's a bunch of images. If I use the slider, you can see these are different orientations of my visualization. And then there's just one variable, right? One phi variable. So if you try to drag theta, it doesn't work because there's just a single value of theta. And so here you can also modify the image size, but that's pretty much it. So it's just a single variable, right? And you can look at this data set from different azimuthal angles. All right. You can also play with it using, so let me quit this. And you can also play with it using a standalone application Cinema. So if I type which Cinema, it tells you that it's coming from this Cinema Sci environment that just sourced a minute ago, right? So you can also use the command line tool, and it will open in a specific browser, right? So for example, Firefox. One thing, and essentially is going to be the same. But one thing you have to remember is that you need to enable viewing of local files inside your browser for this to work. And if you go to the documentation, I actually have a link somewhere in the slides. I'll show you this link later. So depending on whether you're using Firefox, Chrome or something else, you will need to follow the specific instructions to enable viewing of local files for these to work inside, in my case, Firefox. And then optionally, you can also use this in a Jupyter notebook. So it's fairly straightforward. You start a Jupyter notebook, and then you just paste lines like these ones. Personally, I don't like using Cinema inside Jupyter notebook because the view is way too small, and it's constricted to the notebook with all the cells. But if you're a fan of Jupyter notebook, you can certainly use it there. So the the viewer that I showed you so far is called View. There is also another viewer that is called Explorer. And with the Cinema version 1.0, it almost never works for me. So I'm not sure what the reason is. So there is some bug. I'm using it from Python 3.11 on my laptop, and it usually just shows an empty page for me. I'm not sure what it is. So what's supposed to show is a grid. So instead of just showing one image and a bunch of sliders that you can play with, and the image will change, you can also use the Explorer where you load a bunch of images at the same time. They'll show on a grid in your web browser, and then at the top of this web page you will see an interactive parallel coordinates graph with all these variables, and then you can click what range of each variable you want to display, and then it will, instead of displaying all images, it will only display a subset of images. So I'm going to show you Explorer in a few minutes. But for me, in version 1.0, the viewer works most of the time. Explorer mostly doesn't work. Not sure what it is, a bug, or maybe just not compatible with most recent Python. Not sure. So there's another standalone viewer, which I actually quite like. It works great every time, and it's coming from the same data at scale group at Los Alamos. So it's hosted, sitting on this GitHub repository, Cinema View. And the way it works, it's essentially you open a file on your computer, and then in this Cinema directory, you have to basically you have to add this JSON file where you specify which databases, which data sets you want to view. So let me show what it looks like. So I'm going to go to Cinema View, cd cinema _view. And then there's this file, Cinema View 1.1, but on Cinema View 1.1 is called databases JSON. And what it contains is a bunch of databases. So currently, by default, there are two databases that you can load from this website. So there is this sphere.cdb data set that I showed you before. And there is also a CDOF explosion or implosion test. So that's hydrodynamical simulation of an explosion in a dense medium. And notice there are actually three different data sets that are part of the same setup. And then I added a third one. So I added a third one, which is this galaxy formation simulation from Cinema tutorials as well. So they ran a few years ago. They ran a tutorial at Supercomputing. I think if I'm not mistaken, last time they did it into 2020 when I was when I was in person. And actually, no, 2020 was not in person. It was probably online. Yeah. But anyway, so it's a tutorial. It's a data set from the tutorial. I'm going to show you the data set as well in this presentation. But here I just tell that here's where the data set is. Here's its name. Here's the location. And then when I open this page in my web browser, you'll actually see, you'll actually have access to all these data sets. So let me show you this. So I'm going to open the page, open cinema _view.html. And this is what it looks like, right? But here I actually have three data sets now. So there's the spherical data set right here, right, that you've seen before. Then there is the set of test data set. And the interesting thing here is that it actually contains three data sets, right? So these are three different cinema databases that you can view side by side. And so the only trick needed for this is each data set must have exactly the same set of parameters and exactly the same number of frames. So here, for example, I can evolve it in time, right? So there's three parameters, tie, phi, and theta, so two angles, right? So you're gonna spin it in phi, you can spin it in theta, and then, for any of these views, you can view it as time progresses, right? So this is essentially a three-dimensional data set. So a movie, think of an animation as a one-dimensional, sequence of images, right? So this is a three-dimensional data set where you can explore things, any way you like. And then finally, there is this galaxy formation model where, you can evolve this in time, and there are two angles as well, right? So this is this static viewer, which works really well, and it's open source. You can download it from GitHub. There is another viewer that is also open source that is based on Qt. So I haven't tried it. I didn't install it. Well, Qt or Qt library, right? Because I don't have this library installed on my computer. But if you have this library installed as a source on your computer, then you can actually download this standalone viewer and play with it. So I have not played with it because, well, there are already a lot of viewers I have access to. Personally, I like another viewer, which is PyCinema. So that's the Cinema Science version 2.0. Right? And you can install it. So it's also Python library. You can install it also easily via pip install, right? But make sure you do it in a separate environment. So you'll say create a separate environment, and you'll say pip install PyCinema. And then optionally, you can also enable it in Jupyter Hub. But in my tests, none of the included Python notebook examples actually worked. I'm not sure why. They just led to internal Python errors. But the command line tool works really, really well, and it works as a standalone application as opposed to loading everything in your web browser. So for that reason, I like it really very much. So let me show you how to use this PyCinema toolkit. How to use the viewer from this PyCinema toolkit. So let me go back to my command line. Then I'm going to activate version 1.0, and then I'm going to source the PyCinema environment for Cinema Science version 2.0, right? So being activate. And then all I need to do is, let's see which direction. I'm in Cinema View. So I'm gonna show the same sphere. So I'm gonna say Cinema. And this time it's really very easy. So I'm gonna say Cinema View. That's all. You don't need to specify the port. You don't need to specify the location. Well, -D for the database. Don't need to specify the browser. It just opens in a standalone application. So all I need to do is just point it to the data set. So I'm gonna say Sphere CDB. And it opens as a standalone application. So let me make it bigger. But it's very similar to what you've seen before. It's just it runs as a standalone application, and I really, of all the views, I much prefer this one. And also here, so another option here is instead of launching the viewer, you can also launch the Explorer that will give you these parallel coordinates graph at the top or maybe on the side, and then you can select what range of coordinates you want to view your images for. So all you do is just say Cinema Explorer, and point it to the data set. And this is what it looks like. So here we have just a single parameter phi, right? So here, let's say we're interested in this range of phis, and it just gives you, a selection of phis, a selection of images for these values of phis. Let's say I want to see this range. Well, here it gives you a range. Maybe you're interested in a single value, and so on. So basically, just highlight a range. If you have a single variable for a single variable, if you have multiple variables, you will, can highlight individual variables on this parallel coordinates plot. And it's interesting that you can get some similar functionality with the previous viewer, so Cinema View. If you go back to the View viewer, so here, if you switch from the slider to viewing individual objects, so here you have these. I'm not sure if I can resize it, probably not. So here you can actually, highlight the range or the values that you wanna show, right? And then it will show just the images corresponding to those specific values of phis that is selected here. Anyway, so this is all I wanted to say or say about the viewers. So there is quite a selection of viewers. I personally like this standalone viewer, which just opens a web page, but here you need to enable viewing local files in your web browser. And then usually I just use this PyCinema toolkit because it's so easy to use. It opens an standalone application that you can resize very easily. So now the important question is, of course, well, it's great, but you need databases, right? So how to create these databases? So the rest of my presentation is going to be centered on that. So I'll start with the canonical approach, creating cinema databases via extractors in Paraview. So Paraview is this open source tool that we teach and love for visualization. It's really great. It works on multiple platforms. It can run on a laptop. It can run on supercomputer in parallel. And anyway, so let me show you an example that actually comes from this from the cinema tutorial from Supercomputing 2020. I think it's a very nice example. You've seen this already, so that's the galaxy formation simulation, but I'm going to start with the actual VTK files. So VTI files are VTK files for image data, right? Basically, it's data on a Cartesian mesh. So in this data set, there are 18 time steps, and I'm going to visualize it in Paraview. So let me start Paraview. All right, so here's Paraview. If you cannot see Paraview, let me know. And then what I'm going to do, actually, let me drag the slides to a different screen so I can actually see the instructions at the same time as I demoing this. So I'm going to open these data sets. I'm going to go to File, Open, and then in TMP folder, I download this. It's also on GitHub, and there's a link in the slides. So I'm going to go with this tutorial data. I'm going to go to Data, to NX burning density. So this data set, the cinema folks use for their tutorials, I think it's a very nice data set, not too big. So I'm going to load all these files as a bunch. So there are actually 18 files. So there are 18 data sets. And I'm going to load all of this as a sequence, right? So when I do this, here the load, if I go to Information Panel, I scroll down, you will see in time, there are actually 18 frames that were loaded. So index from 0 to 17. And then I'm going to go, let's just create some very simple visualization. So let's go to Surface, color by the burning density. So here I can create any visualization I like. So I'll just, look at the outer surface of the box. But if you want, you can create a contour plot or anything you want, right? But the idea here is that here we create a visualization. We can actually play it back in time. So here is, here are different images, right? And I can actually spin it as it plays back. So here we have 18 time steps, and what we're looking is burning density in this galaxy formation model, right? Okay, let me go to the very first time step. And now I'm going to create an object called, so I'm going to apply a filter, well, not a filter. I'm going to create an object that I call this extractor. So I'm going to, in my menu, I'm going to go to extractors, then image, PNG, and it creates a PNG extractor. And what it is, it's essentially, think of it as a writer in your visualization pipeline, right? So here I read the data, then I visualize this data somehow, and then I create an extractor. There's a question, because images that have been used in an example will assign a numerical value. We could use the slider to choose the image that we wanted to see, yes. If my images files do not have a numerical value assigned to each file, can I use, so the answer is yes, and I'll show you exactly that in a few minutes. So yeah, just wait, but the answer is yes, absolutely. So what we'll need to do, in addition to images, you will need to create this CSV database file. And so this is what my, essentially the rest of my presentation is about, how to create these databases. So in this example, I'm going to show you how to do everything in a single step, so via extractors. But in the following example, I'm actually going to show you how to do it from a set of images. So exactly a question. Yeah. All right. So here I created this extractor, and think of an extractor as a writer, right? So here you load your data, and then here you create a writer, and then this writer acts on a trigger. So right here, you can see the trigger in properties, and the trigger is time step. So what it means is that basically, if you have many time steps in your data sets, in our case, we have 18 time steps. So every time ParaView renders something, loads a new data set, it renders a data set, and then so the trigger is the new time step. So it's going to save this as a PNG image via this extractor, right? So, and another thing that I'm going to change is I'm going to scroll down, and by the way, all these instructions are right here in the slides, right? So if you don't have to write things down, so here are step-by-step instructions in the slides. And then, so here I'm going to scroll down, and under camera mode, I'm going to switch from static to phi theta. And what it gives me, it will give me 6 phi angles and 6 theta angles, right? So this corresponds to rotation around the vertical axis, so azimuthal angles, and then the vertical angles rotation around the y-axis in this case. So I'm going to click Apply, right? And then, so the extractor is set. Then I'm going to go into File, Save Extracts, and then here I'll need to specify the directory into which I'm saving. So I'm going to be saving into the TMP folder. Right now, let me just show what it looks like. Right now, my TMP folder does not have any images. So I'm just going to be saving in there. And then, okay, TMP folder, great. So here I specified I'm going to be saving these images and the database in the TMP folder. And then here, if you want to generate not just the images, but the database as well, so the CSV file, you're going to click on this one, Generate Cinema Specification box, right? So now I'm going to say, click OK, and it's extracting those images. But no, so it's going to take a while because what it's doing is now we have 6 by 6 angles. So 36 angles times 18 time steps. So it's generating 648 images, right? So that means that it will actually take probably a few minutes to do this. So you can see there's a progress bar. And if I show you what it looks like now, you see now there are all these images, but it's gonna take a few minutes. So instead of just waiting for this, because we don't have a lot of time, I'm just gonna kill it, and I'm gonna show you what it looks like after. So let me kill ParaView. Okay. And then let me show you what it looks like when you finish generating these images. So on my computer, it is in the directory. Oops. It is in the directory KSO1. So inside KSO1 directory, here I have this subdirectory. And then here we have, let me just count the number of files there. So here I have 649 files, right? So 648 images plus one data.csv file. And if I look at the data.csv file, you'll see that it will contain 649 lines with the file names. So these are the files that it's creating. And then there are three parameters. So there is the phi angle, there is a theta angle, as well as there is time. So there's also what is called producer, but it contains PNG1. So basically it just says that what we have here is all images. And this column, you can actually delete it. And it's not necessary in this case, but in case if you have different types of images or different types of data, then the producer will contain some other information. But anyway, so here we have three parameters. We have phi that is changing, so you can see that it's changing in degrees. We have theta that is changing, and then we have time, right? And then we have the file name. So time, as I go down, you can see that it changes from time step 0, so these pink columns, to time step 17 eventually, all right? So here we generated everything, just in place, straight from Preview, so we didn't have to create the database files ourselves. And then if I load it into the Cinema viewer, so PyCinema view, I'm going to just say Cinema view, and then case 01, this directory, and then it will open the viewer. So this is what it looks like. So you've seen this already, right? So here we can evolve it in time. We can spin it vertically. We can spin it horizontally. And actually notice that spin here is not exactly horizontal. It's around the y-axis, right? So because by default, when you spin around the vertical axis in Preview, the vertical axis is the y-axis inside your visualization. So here we have, here we're actually spinning around the y-axis. So I'm going to show you in a few minutes how to actually change that. But anyway, so here we created the database from scratch. So in my computer, it takes 2 minutes to do this. And the database contains 648 files, right? So basically for every angle, we have full time sequence. All right. So if I go back to Preview and look at the triggers, so notice that the trigger that I used was called time step. There are also two other triggers. So one of them is called time value. But as far as I can tell, its functionality is exactly the same as time step. So I tried to play with it, and I saw absolutely zero difference between the time value trigger and the time step trigger. So it's supposed to, trigger by when you go to the new time step, but I guess that's by definition essentially the same functionality. And the third option here in trigger, so when you create the extractor and you look at the properties of the extractor, there is a drop-down menu that says trigger. A third one is a Python trigger, and what it does, I have no idea. So if you actually open Preview, let me open Preview, and then you create some simple visualization. Let's just, I don't know, bring a sphere. I'm just creating something very quickly. And then let's create an extractor. So I'm going to go extractor, image, PNG extractor. And then here in the properties, under triggers, properties of the extractor, you see the third one is Python. So presumably you enter some Python script here, but I saw absolutely zero information online. So I tried to go to forums, to Preview discourse, online documentation, and there's no information whatsoever, no mention of this. So maybe it works, maybe it's placeholder for something else. But fortunately, you actually can script everything yourself, in regular Preview Python. I'm just going to show you how to do this very, very easily, right? So, and by the way, camera mode, remember that I said the camera mode in my example to phi theta. So if you use the default value of static, then you will just generate, in the previous example, just generate a one-dimensional sequence of images for a fixed orientation, right? So it won't be generating different views, just a fixed orientation, fixed theta and phi. We just generate a time sequence of, in our case, 18 images, right? So no rotation. All right, well, all of this is good, right? But the extractor is, actually, let me talk about one more thing. So let me actually go back to the previous example. So let's very quickly create a visualization. So let me go to this data directory where I load the data files, and then I visualize them, right? Like this. Then I will create the extract, let's say image PNG extractor, and let's say trigger is time step. And for this guy camera mode, I'm going to switch to phi theta, right? Click apply. So now we created everything. So in my previous example, I would go to File and Save Extract. But this time, I'm going to show how we can actually script all of this and run on an HPC cluster. So in this case, we have the full visualization pipeline. So imagine that this is some fancy visualization. In this case, we're just looking at our service, but imagine that it is something much fancier. And then you create the extractor, right? So eventually, these images are going to be written to disk. And then I'm going to save, going to go to File. And instead of Save Extracts, I'm going to save state. Save state, and then go to TMP directory, going to call it export.py. Okay, so here I'm not sure there was a bug. So now I actually have selection. So .py Python save it as a Python state file. Say OK, and now I just accept the defaults. So here it saved my visualization as a file export.py, right? And if I look at this file, you see that it's a Python script. And then what I do is at the end of the script, you see there's a bunch of things. Actually, let me show the whole thing. At the end of the script is a bunch of things that are properties of my PNG extractor, right? So the file I'm writing and the format I'm writing into, the image resolution, the format, phi theta. So optionally, I can specify some other things. So they are in this slide. So I can specify things like a resolution, for example. So here I specify the phi resolution. To make it bigger, the phi resolution, and then the theta resolution, let's say 10 by 10. Optionally, I can also specify the range of time steps. So let's say I enable selected time steps, and then instead of saving all 18 time steps, I save just the first 3, so 0, 1, and 2. So that's how you would do that, right? So by these, various attributes of the PNG extractor. And then eventually the last line in your script is going to be save extract. So you're specifying, the file path and the file name that you're saving these Cinema database to, and then you're specifying, you're enabling the Cinema database, right? So just checking that, so setting this to 1, and then you have a script, you save it, and then you run it as a Python script. And so the nice thing that you can actually run this on an HPC cluster, right? So you don't need to open ParaView. You can create this visualization interactively on your computer, then create the script via, file save state as a Python script, copy the script to the HPC cluster, edit this, make sure that it works, and then you can run it as a batch job on the HPC cluster without opening any windows at all. Well, so all of this is good, right? Are there any questions so far, by the way? So all of this is good, but so far what I've showed you has very limited functionality, because with extractors that I showed you as, by this, ParaView Python PNG extractors functionality, all you can do is animate in time and 2 angles, phi and theta, and that's it. So as far as I know, well, unless you go to this Python option inside extractors, which has 0 documentation, I have no idea how to use it. You can only animate, in time, phi and theta. There's a question: the values from time for time from the initial data or from the time rendering images in ParaView? So those values are the time steps. So those were integer numbers 0, 1, 2, 3, and 217, right? So they correspond the integer time steps. So they are the data files that I load into ParaView, right? So I loaded 18 time steps, and they index from 0 to 17. So that's what the numbers are for time, right? Anyway, so, but what if I want to visualize other variables? So let's say I want to visualize, I draw an isosurface and I want to play back in different values of the isosurface. How would I do that? So let's say I want to turn on and off various layers. I want to switch to different representation, right? So, there's lots and lots of things you can do in ParaView. So, and all of this, as far as I know, you cannot do easily via extractors. So fortunately, you can do it yourself. So if you want to create a one-dimensional database where you try to animate some variable via slider, you can just use regular keyframe animation. So I'm going to show you in a minute how to do it. If you want to create a multidimensional cinema database, you can actually code everything in regular ParaView Python with very little effort. And I'm going to show you in next example. So let's start with a very simple example where we have we want to create just a one-dimensional cinema database where we just have a slider in a single variable. So let me load a data set called cinema assign envelope.nc. So that's a data set I regularly use for teaching. And let me just start from scratch. So it's a mathematical function, but the nice thing is mathematical function defined in a unit cube, and then I can visualize it very easily. So it's a netcdf file. So basically here I load the data. Here is what it looks like on the outside, right? Oops, sorry, not a slice, but a surface. Here's what it looks like on the outside. So it's a mathematical function of x, y, z defined inside a unit cube. But what I want to show you is I want to create a contour visualization. So in isosurface, let's say, add this value of my density, the single variable called density variable, right? So here's an animation that I actually want to render. And what I'm going to do is I'm going to create an animation view. So animation view, I'm going to be animating counter by the value of density. So the way I draw, basically I'm animating how I position my isosurface, right? I'm going to create a timeline for this and then double click on this. And so here I'm going to select the range from 0 to 2. So as time goes from 0 to 1. So for the duration of the movie, my variable is going to go from 0 to 2, right? And then, okay, great. And then another thing that you probably want to do this is you want to set the custom range, so rescale to custom range, so that the range goes from 0 to 2, so that I'll have nicely changing colors in my animation, right? And then I also want to have 100 frames here. So let's just create animation with 100 frames. And now let me position it like this, and then I'll just click the playback button. So this is what it will look like when I eventually export it into a cinema database, right? And the color here also shows me the value of density, right? So next, actually, I'm going to be exporting into the same directory. So let me just clean things. Actually, no, not in the same directory. Let me create a temporary directory 123. So inside TMP folder. So currently it's empty. I'm going to be exporting into this directory. So here I'm going to say file and then save animation. So not save extract. So there's no extract, save animation that it just showed interactively. And I'm going to go into TMP 123 folder. I'm going to call the individual frames frame, and then there's going to be some number.png images. Let's just save them at full HD resolution, right? And accept the default compression ratio. And here it's saving those images. And so there are 100 frames, right? So that means that there's going to be 100 images, PNG images in the directory. So let me just wait. All right. So here I have 100 images indexed from 0 to 99. And then I'm going to run a script. So here I wrote a very simple Python script. What it does, so when you run this script, you need to pass 3 arguments to it. So the directory containing the images, and then the start value of your variable, and then the end value of your variable. And so what it will do, it will read the directories. Here it reads, actually, let me maximize it. Here it reads this directory, all these images in your input directory, and then it sorts these images, the file names alphabetically. It strips off the paths from the file name, so just left with a list, so Python list of just the file names without the paths, and then it creates a density array starting from the start 0 value to go into the end value of 2, right? In this case, in my example, and then it simply creates a density, a list called density. So, and this is an important part. So it is written out in a fixed value format. So there is a fixed number of digits. So there are only 4 digits after the the decimal point. And this is important because otherwise, when you load this database into PyCinema, if you have a numerical value that has variable precision, then the length of your slider of your slider bar is going to be changing, and then the position of your slider is going to be changing as well, and that's just not a nice experience. So if you try to play back, move the slider, it will just be very jumpy. And so to avoid that, what you want to do is you just make sure that you write in a fixed precision, right? So you will see that in a second. So and then you create here I create a pandas data frame that contains 2 columns. It contains a density column and then the file names column, right? And then I write it, so I take the data from these 2 lists, so files list and density list, and write it into data.csv file. So let me just show how to run it. So this script is called generate single variable.py. So let me call it. So it's in documents, generate single variable.py, and then I pass the directory name. So it's the current, it's the current directory, and then the values 0 and 2. So the starting and the end values of my density. And just goes through all those images, it reads all those images, and then creates this data.csv file. And the file looks like this, right? So it has this density going from 0 to 2, and then the corresponding file name. Okay, so now I want to visualize it. So I have the PyCinema loaded. So I just say cinema view database in the current directory, and it will play it back, right? So here I have just a single variable, and here we have a nice slider, right? But this is of course similar to animation, right? So this is not particularly interesting. What is interesting is you probably want to have multiple variables. So how do you do this? Well, answer is very easily. You do it with Python scripting. So here's an example. Let's visualize the same contour filter, but this time what we're going to do is we're going to create a database where we have 3 variables. So we'll be animating in 2 angles, as well as the isosurface. So it's the same as previous example, but in addition, we'll have 2 angles as well. So the way you do this, in ParaView, you would create your visualization, right? And then you save it as a Python. So I won't show it now, but you go to File, Save State as a Python script, and then that will give you a Python script. Optionally, you don't have to, but optionally you can simplify the script because a lot of parameter values are going to be defaults that you don't have to specify. But anyway, so you'll have your Python script, and let me just show you what it looks like. So here, let me quickly, so it's called generate multivariable.py. Let me just load it here, and I'll make the font bigger in a second. So generate multivariable.py, so bigger font. So this is what the script looks like. And I have an addition to the script, so I commented it out. So here, what is not commented out is just the straight Python state file that was created by ParaView, right? So I can actually take this file, so generate multivariable.py, and run it as a state file. So here I can either just start the ParaView GUI and then go to File, Load State, and then navigate to that file, click on OK, and then we'll just create the visualization. But I can also do it from the command line. So from the command line, let me go to the directory containing the state file, and then I'm going to say ParaView -- state. State is equal to, and then the file is, what's the state file name? It's called generate multivariable.py. Generate multivariable.py. So I'll start ParaView and we'll automatically load the state and we'll show you the visualization. So here's the visualization we are animating, right? So essentially, we want to animate this in 2 angles and then in a contour as well. And so the way I do this, I take the state file and I uncomment these lines. So these lines actually have a slide for this because in my text window, they don't really fit in here. So I'll just show the slide. So it's exactly the same code. So here I just simply added, custom block at the end of my ParaView Python state, just standard state, ParaView Python state file, where I create this multidimensional cinema database. So here I have 3 parameters now: the phi angle, the theta angle, and a contour, right? So phi is, I'm using 50 angles for the horizontal rotation, 3 angles for the vertical rotation, and then I have 5 contour. I have 5 contours. And then I create this initial list of the values of phi, theta, contour, and file names that will go into my my CSV file, right? And then I simply generate the initial, the array of densities that go, let's say, from, actually, I should probably have from 0 to 2, right? Or maybe, no, actually, yeah, any values here, fine. So in this case, in this example, I have 0.1 to 1.9. So in 5 steps, and contour is equal to 5. And then I have 3 nested Python loops, right? So here, the first loop is going through all theta. So I have only 3 values of theta, right? So if J is equal to 0, elevation is 0. So this is a camera-centered view, right? So we do not tilt it vertical. We just look at, straight on, from the equatorial plane. Then if J is equal to 1, we have the camera below track. So tilt is a variable that is set to 35 degrees. So I'm going to say my camera is now sitting 35 degrees below the equatorial plane. So looking at my visualization from below, right? So elevation is set to minus tilt. And then so here I set up, this is optional, you don't have to do it, but I prefer to have rotation not around the y-axis in my visualization, but around the vertical vector in my screen, right? So it's actually rotating like this, horizontally in my view. So in this case, I actually need to set up manually the view up vector, which by default is the y-axis, but I want to be this view up vector in the plane of my screen. And then if J is 2, do exactly the same. So previously we were at minus 35 degrees, now elevated by 70 degrees. So now we're at plus 35 degrees, right? So set elevation variable to plus 35 degrees. Again, adjust the view up rotation vector. And then we have a set of n phi angles, so 50 n phi angles, where azimuth, so if I is equal to 0, initial azimuth is 0, and then if it's not, if it's greater than 0, then rotated my visualization horizontally around the vertical axis by this angle, right? So 360 degrees divided by 49, right? So that the full visualization will correspond to full rotation of my object around the vertical axis. So adjust the azimuth variable, and then here finally I go through, so 3 nested loops. Finally, I go through the density, and then eventually I create a new file name, right? So with a counter, save the screenshot into a specified directory, and then I'm going to say here I create I append the value of azimuth to phi list, append the value of elevation to the theta list, append of value key density to the contour list, right? And then I also append the current file name to my files list. So now I have these 4 lists that are right into a PNG file. So now if I were to run this, this will take probably around 5 minutes on my laptop. So I'm not going to do it live because we are short on time. But here's an example of the output. So the output is in case 4. So let me go into case 4 on my laptop. And this is what it looks like. So 750 frames, right? Because we have, so let's see, we have, oops, we have, so 55 angles times 3 vertical angles times 5 contours, and that gives us 650 angles. And there should also be the data. Yeah, there's also the data CSV file, which simply contains 650 lines for describing those individual images. So now if I load this into PyCinema viewer, so oops, sorry, I'm going to say Cinema and then view the current case of 4 directory, this is what it looks like. So now I actually have a multidimensional database where I have 3 sliders. So I have angles, right? So for vertical angle, I have just 3 values as described. So camera below, centered camera, and then camera above you. I have 50 values of angle, right? So even for, for every elevation like this one, I have 50 angles, and then I have 5 values of my contour. Okay. So here we go. And then if I were to switch, let's say, to an object view, you can certainly select, things that you want to see, only a subset of things, or optionally, instead of using the viewer, you can go to Explorer, and so here it actually it will present a nice view here where you can select a certain range of, let's say, angles, a certain range of these guys, and so on. Right? So it's just a little bit slow because there's a lot of images that is processing, but you get the idea. So you can actually select a subset of images. So this is how you would. Oops. Oops. Let me just kill this Explorer. Yeah, right. So this is how you would create a multidimensional database using Python scripting from scratch. So really, really easy. And the final example I'm going to show you, we have only 5 minutes left, is a more complex case where instead of animating 2 angles and a counter, for the same data, I'm animating a layer on and off, material selection and osprey, as well as an azimuthal angle. So first of all, so here I already created a Python. So I create my visualization. And then I created a Python script called glass.py. So let me show what it looks like here in my text editor. So here's glass.py. So if I comment out all the lines at the end, I'm going to show you in a minute, and just show you the visualization itself without my customized block. So let me load this into ParaView. So I'm going to go to Documents, this directory, I'm going to say ParaView --state is equal to glass.py. And it will load ParaView, and it will switch to Osprey ray tracing. So you see there are nice materials. So now I have contours drawn as a glass surface. And so here in the properties of Osprey, if you scroll all the way down, you see one of the things is multiple passes. So right now, samples per pixel. Right now, samples per pixel is set to 1. So that means that it produces fairly grainy visualization, right? So you see lots of grays, lots of noise. So if I were set it to let's say 30 or 50 or 100 samples per pixel, it'll be much nicer visualization, but it will stop being interactive, right? So I won't do it now. It'll just become very, very slow, but it'll produce much nicer images. But you can, of course, do all of this via Python scripting. So what I'm going to be animating is, first of all, I'm going to be animating this block on and off. So here we have a couple of clips, and I'm going to be animating clip on and off. Then I'm going to be animating the contour. Contour, and the way I'm going to be animating is I'm going to be switching between 2 different surfaces, so a metal surface and a glass surface. And then I'm going to be animating, so the third one, I already forgot. The third one is going to be an azimuthal angle. So what I do here is so visualization that you just saw, I create a Python, just save it as a state file, and then at the end of this file, I append the following script. So here we have 3 variables. We're animating in phi, in the clip on and off, and then in the selection of material. And then I have 3 nested loops, right? So here you see that if I go to my Python script, so here I just, uncomment this script, and then I run it. But of course, oops, sorry, uncomment. But of course, there are lots of combinations, right? So there are a couple of hundred images, so I won't do it live. But what I'm doing here is, so the first loop is goes through two clip states, so either show or hide. So by default, it is shown, but then second loop iteration, it's, if clip state is hide, then hide the clip. Then for composition, I switch between two values, so two materials, thick glass and this metal lead brush material, right? So here I simply, one of the properties for spray material. For the contour, I set composition, which is either, this value or this value. And then I go through all 50 and 5 angles, right? So, and then I create the files, the images, save the images, and then I, fill in, so append the row to my database, to my pandas data frame, and then I save this pandas data frame as a .csv file, right? So when I look at this, so the example is in case of 5. So let me go into case of 5 directory. So this directory contains 200 images, so all those combinations, as well as a data.csv file. So let me load this into the viewer. So here is what it looks like. And then you have the, as usual, 50 angles, right, as before. Then you can turn the clip on and off, right? So here's just an example of, turning on and off a layer. And then here you can switch between different materials. So we have two materials. We have glass and metal lead brush material, right? And of course, you have a full combination of all of these guys, right? So you can explore, any combination you want. But you get the idea, right? So you can script pretty much anything and then save it as a Cinema database. So are there any questions before I show the last slide, and then we'll pause? Oops, let me go to here. Actually, almost the last slide. So yeah, so general thoughts so far. So notice that if you have multiple variables, you want to have multiple sliders and multiple variables, then your number of images can actually grow very quickly, right? So consider a case where you have, let's say, a bunch of parameters. Two of these are phi and theta angles. So let's say you want to do 30 phi angles and 30 theta angles. So that gives you 900 frames for every combination of the rest of your parameters, right? So if you have a few additional parameters, the number of frames can grow easily to tens of thousands. And of course, this is not really manageable. Not only it will take a very long to render, but also it will use a lot of disk space. So my suggestion in this case, instead of going crazy on all parameters, try to, instead of animating in two angles, try to animate in a single angle. So in practice, I find that it works really well. It still gives you, multiple orientations, let's say 35 angles, and then just have a single select, just a single, theta angle that you want to view. So that'll reduce the number of images. And then a litmus test is probably, a good test for whether you are going overboard is compare the size of your original data set to the size of your output Cinema database. So if your Cinema, if your original data set, let's say, a few hundred megabytes, and your Cinema database is 30 gigabytes, then probably you have way too many parameters, right? And maybe in this case, if a data set is not that large, you can actually do everything interactively, and you don't even need the Cinema database. But the point here is that you can actually script everything that I showed you so far, and you can run it as a batch script on a HPC cluster without opening any windows, right? Submit as a Slurm job, and at the end of the job, you will have a nice Cinema database. So my very last slide, we are out of time. My very last slide, just a quick comment on ParaView Catalyst. So ParaView Catalyst is this library that lets you instrument your simulation code to output, well, basically to expose the data arrays in your simulation code and to do rendering live from these data arrays without saving them to disk. So essentially, it's live rendering using ParaView scripts from inside your simulation code. And I gave a webinar on this exactly 1 year ago. So in September 2022. There's a link from the slides to that webinar. You can find it there. But I won't go into the details here. The point I want to make is that when you instrument your simulation code with the Catalyst library, and then you create your, you take your representative data set, which is a data set that is similar to what is going to be produced by your simulation. Then you load it into ParaView interactively, and then you create an extractor, and then you go to File, Save Catalyst State, so that will create an image that you will pass on the HPC cluster to simulation code to actually generate a bunch of PNG images that correspond to, well, that basically take data live from your arrays at simulation time and save them, render them and save them as PNG images. So the point here is that when you go to File, Save Catalyst State, there is a checkbox for generate Cinema specification, basically output all these images in a Cinema format, right? So add the .csv Cinema database file to them, and then you'll have a nice Cinema database at the end of this. So I'm not going to show you, this as a demo because there's actually quite a steep learning curve when it comes to ParaView Catalyst. But the point here is that you can actually, everything that I mentioned before, you can use inside Preview Catalyst, and it's fully compatible with a Cinema specification. So I think I will stop here. I will just show this slide and pause here for questions. So if you have any other questions, please let me know. Yeah, so Cinema, I mean, it's really fun. It's if you try to research this on your own, it gets confusing very quickly because there are just so many projects and so many viewers. But hopefully this webinar made it a little bit easier to navigate that. So there are a couple of really excellent views that I recommend. One is the standalone view that I mentioned before, just a website where you edit a JSON file, and the other one is PyCinema or Cinema Science version 2.0, the same thing. And use it from command line, works really well, at least for me in all my tests. And yeah,